All right, I can see one of our students over here has everything set up just the way that I'm hoping to see it. So that's good. So that means we should begin. All right, so welcome again. So we're doing Math7502, Data Science, Introductory Mathematics, basically linear algebra as it applies to preparing oneself to do data science. Okay, so I'm saying that because this is going on YouTube, and YouTube likes to have a good introduction to draw people in. So, okay, now what we're doing today is we are going to cover solutions and talk about solutions to the quiz that you guys have already done in Math7502. Now, did you do the quiz? Yes, good to know. How did you find it?
Not very easy.
Not very easy? Well, there are easy bits and there are not so easy bits. Okay, that reminds me, I should try to open up the chat here so I can see what's going on with everyone else. Okay, so I see, well, I shouldn't even try to pronounce these names. How about Chen? Hi, Chen, how are you? So Chen is somewhere else in Zoom. So would you guys on Zoom, guys and girls on Zoom, just give me a hello? Yeah, you, Chen, I'm just saying hi. Okay, just give me a hello that you can hear me okay and see everything that I'm doing. Hello, good, great. We're live. Okay, so let's begin. Now we're doing this quiz. You probably find this familiar, but I've written it out by hand just because I felt it would be easier than going and printing it out. Okay, so the first question of 3 questions of this quiz says, consider a function mapping R2 to R2. All right, so this is just pairs of real numbers, mapping to pairs of real numbers. And the map is explicitly given by this rule. So we send the column vector uv to this column vector with u's and v's in it, and then we have an exponential in there. All right, then we define another function g of x, sending the same set, but this time to a different set. It maps to the set of, well, quadruples of real numbers, but we can interpret this as 2x2 matrices with real entries. Okay, so that's how we'll view this, but the map is explicitly given by g of x is equal to f of x multiplied by the row vector, or 1x2 matrix, 1, 2. Then we have a definition that z is equal to 1 minus 1. Okay, so part A says evaluate f of z. Well, this is easy, all right, but I'll begin to do that. So f of z, hang on, let's make sure my pen's in good order. Okay, f of z is equal to, now we're just substituting in the values 1 and minus 1 into the function there. So this will be easy. So we've got 1 times minus 1 squared plus e to the power of 1 plus minus 1 in the first entry. And then down the bottom, we have 1 squared times minus 1 squared. And we simplify this. Okay, so the first part is just 1, and then we're adding e to the power of 0. E to the 0 is 1. So we have 2 at the top, and we have 1 at the bottom. Everyone agree? Hopefully you got some marks for that if you did this. All right, so let's have a look at the next one. Evaluate g of z. Okay, g of z. Remember that's equal to f of z by 1, 2. Okay, but we already have f of z. F of z is 2, 1. That little pencil that's hanging around on the screen is a little bit annoying. I don't know how to fix it. Actually, if I do anything, I'll probably stuff up the entire dot cam. And that wouldn't be good, so I better just continue. Okay, so 2, 1, we already know that, and then 1, 2. Okay, well, we need to simplify this. Okay, so this is going to be a 2x2 matrix here. So let's just simplify this, and I better use all of the real estate on the page here. So it's a 2 by 2 matrix, so I'll make space for that. All right, now it's 2 times 1, goes in the top left entry. And then 2 times 2 is 4. Okay, and then 1 times 1 is 1, and 1 times 2 is 2. All right, so we're done with that part. Another easy marks. I don't know how many it was, but easy marks. All right, next one. Evaluate the norm of g of z by z. All right, so I'll rewrite this, g of z, and we're taking the norm. This will just be the Euclidean norm. Okay, so we already have g of z right there. So we're taking the norm of something that has now a matrix in it. But remember, when we multiply this by z, we're going to get a 2 by 1 matrix, right? And we can take a norm of that. All right, so 2, 4, 1, 2, and then we put in z. But don't copy that one down because remember z is 1 minus 1. All right, great. So now we multiply this. We still need to write the symbol for the norm. But now let's see, 2 times 1 plus 4 times minus 1. So that gives us minus 2. And then 1 times 1 plus 2 times minus 1. Well, you add those together and you get minus 1. Okay, so now all we have to do is just take the Euclidean norm of that. And so that's the square root of minus 2 squared plus minus 1 squared. So root 5. Okay, and that one's done. Let me check my pockets for another pen. This one's a little bit annoying to use. All right, all good. Okay, so that was C. Now let's do D, which says to evaluate the inner product between the columns of G of Z. Now, sometimes this is called a dot product. Actually, that pen's no good either, but I think I can just play around with this one to make it okay. And before anyone offers me one, that's kind of you, but I like my own pens. So that's, no, this one's good. Thanks, Wally. You can set it there in case it's really bad, but thanks very much. And they do look a little like my pen, so it's not too bad. Okay, evaluate the inner product. So we could write this with this L Langle bracket. In LaTeX it's called, I think. Now we want, I'll just put G of Z, and then I'll put a subscript around that. And I'll just say right now that I mean to refer to the first column. Okay, and then let's do the same, G of Z. Bracket, I mean to refer to the second column. So this is a typical notation for inner product, what you might know as dot product. Okay, now let's have a look at our columns of G of Z. That was G of Z right there. So we're taking the dot product of 2, 1, and 4, 2. And remember, that just means to multiply across and add the result. Okay, or you could take this as a matrix multiplication, right? And you get the same thing, just in a 1 by 1 matrix, but that's often just thought of as a number. Anyway, so here we go. So 8 plus 2, and we get 10. All right, good. So far, so easy. Now, the next one says, determine the determinant of G of X, and why is that independent of X? All right, sure. So I'll turn this upside down to get a little bit more space that I can put right under here. All right, so det of G of X. All right, now G of X, remember, is f of x times 1, 2. All right? But let's just, okay, hang on. So det of f of x by 1, 2. All right, and now, well, I'll just write what f of x would be just to clarify. Okay, so we've got det of, now if I've got an x there, this is taken to mean a vector here, the x, and the rule was up here. So I'll just use I'll say let x be x1, x2 in its entries, all right? And then I'll just copy this down. So what we're looking at here is x1, x2 squared plus e to the x1 plus x2, and then down here x1 squared, x2 squared, all right, and then we're multiplying this by 1, 2. All right, but now I happen to know that this is going to simplify a lot if I abbreviate these. So let's say that this one here, we'll call this one top entry, let's call that y1, and let's call the bottom entry y2. Okay, just to simplify this, because if we don't, it'll get a little bit too big on the page, right? And if you were taking an exam, you would want to save space and time. All right, so det of y1, y2, and then 1, 2. Okay, so we'll expand this product right here. Now we're going to get a matrix, right? Yeah. Right, of course, because we're taking determinant. So this will be y1 times 1 in the first entry, and then 2y1, and then we have y2 and 2y2. All right, and now I think at this point it's pretty clear, because you can see that the first row is parallel to the second row. All right, they're multiples of one another. In other words, these are linearly dependent rows. Okay, so this determinant here is clearly 0. All right, and we can see that is independent of x, because when we abbreviated x as, or when we abbreviated f of x as y1, y2, it didn't matter what the entries were, right? Because we've used arbitrary letters here, and so it didn't depend on x. All right? I hope you're convinced of that, but let me know if you're not. All right, so let's move on to do F. All right, so F says calculate the Jacobian of F. Okay, so we'll first write the formula for the Jacobian. All right, now since F has U's and V's in it, rather than writing this in terms of X's and Y's, we'll write this Jacobian in terms of U's and V's, just to make it clear to calculate and see. All right, now, so the symbol that I like to use for Jacobian is I just put a J and then I put the function down as a subscript, but I'm sure that this is not conventional. All right, and then up here I put in what I'm evaluating that at, okay? So I'll just keep it as UV, right, just to keep that clear, right? So I don't have to go back and forth between two sets of letters. All right, now the formula for that is, so I need a partial derivative in terms of the first letter. And remember, we're keeping this as U. And then over here, I need a partial derivative in terms of the second, well, with respect to the second letter. But what I put that I'm taking it of is the first function. All right, so I'll put F1. Now, F has two parts in it. So I'm going to call this one F1 and that one F2. All right. So F1 goes there, and then here we have a partial derivative with respect to U, and here we put F2, partial derivative with respect to F2, and that's with of F2 with respect to V. Okay, so now that we have the formula for that, we can calculate. All right, so, well, I'll just write it out. This will be a bit big and will take some time, but I think it'll be clearer for you. All right, so And then the F1 is uv squared plus e to the u plus v. So I'll rewrite that here as well. All right. Whoops, that's a u. And now I put in F2, which is u squared v squared. Whoops. U squared v squared. And now I calculate this Jacobian. Okay, so we just simplify this. Now we're taking everything else treated that's not under here as if it were a constant when we calculate this. So what we get is v squared for the first part, right? And then the derivative of e to the x is e to the x. So we have plus e to the u plus v there. There's a chain rule to apply, all right? But the derivative of the exponent is just 1. So it comes out just like that. All right, now we're differentiating the first function with respect to v partially. And so here we write 2uv, and then we again have e to the u plus v. All right, now we're on the second row. So we're differentiating with respect to u. So we have 2uv squared. And then here we have 2u squared v. Is that right? Okay, I think so. All right, and so we've done that. We found the Jacobian of F. Now the next question here says, solve for x superscript 0. All right, where we're taking a linear approximation. All right, so we've got this function f with a hat on it, and it's given by this expression where we have the Jacobian here. All right, so let's first write out that. Well, actually, what I want to do first is I want to sub 1 minus 1. In other words, I want to sub in z into the Jacobian, right? Because that'll be simpler. So let's do that first. And we are doing g. All right, I've taken a bit of time, but I think it's okay. We'll accelerate a little bit through the rest. Okay, so g, we want Jacobian of, so 1 minus 1, and we're just subbing in here. So we have 1 plus e to the 0, and then we have minus 2 plus e to the 0, and then we have 2 and minus 2. All right, so we simplify this and we get 2 minus 1, 2 minus 2. Great, okay, so our next step is to use this formula right here and sub in the rest. All right, so what we have next is f hat of x1 superscript 0, x2 superscript 0. I'm too low. Yeah, thanks, Walla. Okay. And this is equal to f of z, but we know that that is 2, 1. And then we have our Jacobian matrix, so 2 minus 1, 2 minus 2. And then next we have x minus z. So x1 superscript 0 minus the 1 in the first entry of z. And then x2 superscript 0 plus 1 because we're subtracting minus 1. Okay, so, and actually, yeah, I need to solve for this equals 0. I didn't say so earlier, but we're solving for this equal to 0. Okay, great. So that means then that if I were to solve this, then, hang on, I'm a little bit lost. Oh, I see. Okay, so I want to move this over, don't I? I want to move this over to the right-hand side. I want to expand part of this, and then I just want to solve a linear equation. All right, so that's what we'll do here. All right, so the first step, we'll take this vector over to the right-hand side, and so we'll have -2, -1. Okay, but what we also have, so let's just rewrite this matrix, 2, -1, 2, and -2. And then I want to put x1 superscript 0, x2 superscript 0. All right, but there's another part of this, right? The -1 +1 there. And so I want to keep this on this side, and then I want that other part of it on the other side. So when I take that other part to the other side, I'll have to change the sign of this and this, right? Okay, so we'll write that as 2 -1, 2 -2 multiplied by 1 -1, and then we'll be adding that. Okay, all right, so this simplifies. On the right-hand side, what we have is 3 and 4, and then we have a plus -2 -1. Okay, and so we simplify that, and we get 1, 3. So what we're looking at then is this equation, 2 -1, 2 -2, and then our vector x that we're solving for. And so this is now a nice simple linear equation. All right, so let's just finish it off. And I can do it by hand. I don't need to go into Julia. Remember, this is your quiz, so you should have been able to do this by hand. All right, so one way to do this would be to Gaussian eliminate, right, or row reduce the system. All right, that would be fine. Also, you can just take the inverse of the matrix and multiply by it. I think I'll just do that. So the determinant of this will be -4 + 2, which is -2. All right, so x0 is equal to 1 over -2, and then I have the 1, 3. All right, so I'll swap these two, and I'll put minus signs here, okay? All right, now all I have to do is multiply this, and we have -2 + 3, so we get 1 there. So -1/2, 1. And then in the bottom entry, we have 6 - 2 is 4. Okay, and that's pretty much done. Of course, you can multiply the -1/2 in if you want, but you don't have to. All right, so I think that's question 1 finished now. All right, great. So that brings us to look at question 2. Let me just have a look at the time. 25 past, that's not too bad. All right, I'll put that up at the top. All right, so our next question says, let A and B be upper triangular. Calculate E subscript n transpose times AB times EN. Now, that's just the vector with zeros in it until you get to the last one, and there are 1, 2, 3, n of these entries. All right, so it has length n, but the last one has a 1 in it, and so this is the transpose version, so I can nicely fit it in the row. Okay, now if we have 2 upper triangular matrices, we want, well, there are a couple ways to do this, but one way that I personally don't mind is to just multiply out A times B. Of course, you can make other observations, but we'll come to that once I've shown you. Now, what I want is a pattern, all right? So I'm going to write A equals A11, A12, and so on. And then we have a 0, and we have ... 0. Then we have an A22, ... dot, dot, dot. Up here we have an A1n, and here we have an A2n. Then we have zeros below the diagonal, and then we have zeros all the way until we get to ANN. Right now, the matrix B looks just the same, except for rather than where I have the little lowercase a, you would have a lowercase b. Now, the product of two upper triangular matrices will be an upper triangular matrix. Okay, so that's helpful to know. Now, I want a nice pattern for the product AB. Okay, but to help me see that pattern, I will deal with two 3x3 matrices because that'll be sufficient to show the pattern. And I'll just write that here. So let C, I'll just put 3x3 equal A 3x3, B 3x3, and let's see exactly what that looks like. So since it's upper triangular, we have A11, B11, and then we have 0, and then we have 0. Here we're just looking at 3x3s, so we'll have a 0 there as well. All right, and then we'll have an A11, a B12 plus A12, B22 there. And then over here we'll have A11, B13 plus A12, B23, and then plus A13, B33. All right, so that's our biggest entry there. In the middle, we have A22, B22. Down here, we have A33, B33. And here we have A22, B23 plus A23, B33. Okay, now I can see a pattern in this, right? So this has two summons, this has three summons. But if you look at these, let's see, the middle ones are the same, middle same, and then the outer ones, there and there, they have the same subscripts as C12 would have in that position, you see. So that tells you that what you have here is an abbreviated form of this, where you have a sum, you have AI, K, BK, J, all right? And in the subscript, I'll say that this is an n by n matrix, all right? Because I'm generalizing what's here. So I'll just write generally, right? And in other words, not 3x3, but the sum goes from K equals I, and it stops at J. Okay, so that actually accommodates the zeros as well. Okay, so now we can take the product, so E n transpose C n by n, E n, all right, because we have the formula here for C n by n. Now, I really didn't have to do all that, okay, but it's kind of just for your interest as well. So what we'll look at first is this first right part of it, okay? So in other words, we'll have E in transpose, and then let's calculate the product of the two right matrices, all right? Because remember, this one has 0, 0, 0 all the way down to 1 at the end, all right? So when you take the product of, say, something like this times 0, 0, 1, well, what you end up with is just the last column, right? You just end up with the last column. So in this case, what we have here is this simplifies quite a lot. So I have the sum up to n, k equals I, AI, k, b, k, n, and then this is an n by 1. All right? Okay, but it gets better. All right, so this one here, remember, is 0, 0, dot, 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 1. Okay, so when you multiply this by this column matrix, Well, what it does is it multiplies 0 and adds 0 plus 0 plus 0, and then just add the 1 times the last entry. But we know what the last entry is. It looks like this, right? Okay, so this comes out to be ANN BNN. Okay, and that is still a matrix, but it's 1 by 1. All right, all good? So again, I mean, there are other ways to do that. So you could have just made the observation, but you would have had to have justified that properly mathematically, you know, in some well-written words. All right, so let's move on and have a look at the next question. All right, now, so this is the last question on this quiz, but I'll just let you know now that it won't be the last question that I do, because after that I'll do a question or a problem that Yoni suggested that we do on rotation matrices. So that will be what we'll do after this question, because this one won't take very long. So yeah, like I said, we'll construct rotation matrices after that. Okay, so this one says to basically prove the parallelogram law. All right, but you can view it 1/2 the norm of, or the square of the norm of u plus v, 1/2 the square of the norm of u minus v, minus the norm squared of u, minus the norm squared of v, equals 0. Okay, so we've got to prove that. But one key ingredient was the observation here that the norm of a vector x squared is equal to x transposed by x. All right? So we'll use this, right? This will make quick work of the proof. So the left-hand side, now what I want to do is I want to deal with twice this because I think it's just arithmetically somewhat easier. Okay, I don't have to worry about the halves. So I'll multiply through by 2. All right, so then I'll deal with u plus v squared plus u minus v norm squared minus twice norm of u squared minus twice norm of v squared. Okay, this is what we're going to expand using this. So put my equals underneath because it's big. All right, so what we have is u plus v transpose times u plus v. And then we're adding u minus v transpose u minus v. And then we're subtracting twice u transpose u, subtracting twice v transpose v. Okay, good. So let's simplify this. Now we can bring the transpose inside. Okay, so that's next. Bring the transpose inside. Plus u transpose minus v transpose, u minus v. Okay, great. Now we just expand. So we have, from this one, we get 4 terms, remember. All right, so u transpose u, and then we could write plus u transpose v, and then plus v transpose u, and you have to keep the order as they come, right? And then plus v transpose v. All right, so that's this one that I've underlined. Now the next one, this one right here, double underline. That one I'll put straight underneath it, all right? It's already getting big, but it'll be convenient because they're so similar to put it straight underneath. And all you can see that what changes when I write this is that the middle 2 terms will be negative, right? And the others positive. So we have plus u transpose u, and minus u transpose v, minus v transpose u, and plus v transpose v. Okay, but let's not forget these 2. So we have minus 2 u transpose u, minus 2 v transpose v. And if you're quick with your sums, you can see that it's already 0, right? But I'll just do some canceling. Okay, so we can cancel this with this because those are the same, but opposite sign. And likewise with these, we can cancel. And we have 1, 2 of those. We have 1, 2 of those. And so everything adds up to 0. Are you convinced? Yep, okay, and that's a 0 vector, so I'll put a tilde under that to emphasize. Okay, so that's the quiz done. Let me have a peek at the time. 5:37, that's excellent. Good timing, Sam. So I'll put this away because I'll need that fresh and clean to do this again in the next one. And I'll find the papers I need to talk about what's next, okay? Because I've got a plan for what I want to talk about with this. Okay, so what we're doing is we are first constructing a rotation matrix. And I'll just say 2 by 2. We're going to stick to 2 by 2 here because there's enough to talk about with 2 by 2. Of course, you can rotate things in a 3-dimensional space too, right? It just adds complication, but once you understand 2 by 2, well, you can then hopefully think geometrically and write some algebraic expressions and come up with the same for 3 by 3 and so on. Okay, so you've been talking about with Yoni linear transformations, right? So you could think of those as sending points or sending a point to another point via the multiplication of a matrix with numbers in it, all right? And they have some nice properties, right? But this time we're talking about rotation, okay? So since we want to come up with one on our own, so let's let this rotation matrix, let's A theta, so I want to rotate by theta. Now rotations are by default counterclockwise, right? So we'll be rotating counterclockwise an angle of theta. Okay, so let this be equal to P Q R S, and we want to work out what that is. Okay, but we need a good diagram, okay? And I want to keep this simple, so I'll make the simplest diagram I can think of without oversimplifying it. So I'll draw a diagram here, and then I want to put a point, the point C, 0 there. And let's imagine that I want to rotate this point through an angle of theta, and let's imagine that it ends up, we're going to judge this properly, it ends up here at the point A, B. All right, now I know that it should have the same distance, right? If you've ever rotated, I'll just show you with my pen here, right? If I'm taking my pen and I'm rotating it like this, well, the length of my pen hasn't changed, right? So I know then that the distance here from the point AB to the origin has to be C. All right, and that's why I've chosen the letter C, because it makes a nice, well, it works well with Pythagoras' theorem, right? Okay, so let's put a dotted line here and introduce another point. So I'll put in A, 0, because it has the x coordinate of A. All right, that makes the length down the bottom here equal to A. All right, now this point here is B, the y coordinate is B, so the length of this will be B. Okay, good, and we know that A squared plus B squared is C squared. All right, but we're missing one thing, that's the angle theta in there. And let's just draw an arc, because just to remind that that's a circular section there. Okay, great, I'm happy with that diagram now. So remember, I'm multiplying the matrix A theta by C0, and I'm getting AB, all right? So in other words, PQRS times C0 is equal to a B. Okay, great. So let's multiply that out. And so if we multiply the left, well, we have P times C plus 0. So we end up with P, C. All right, the bottom one, R times C plus 0. So R times C, and that's equal to A, B. All right, so now we have our P and R straight away, right? Because, so from this, we get that P is equal to A divided by C, and R is equal to B divided by C. Okay, but if you look at the diagram, you can see there that A divided by C, that's a trig ratio, right? So that's adjacent over hypotenuse, which is cos theta. So just write in here cos theta. Now, can we do something like that for the letter R? So B over C, well, that's sine theta. Okay, great. So we're nearly there. So what we've deduced so far is that A theta is equal to cos theta, and then down in the bottom row, first entry, we've got sine theta, but we still don't have Q and S, right? All right, so what I want to do next is, I don't want to complicate my diagram, and I've already chosen a very simple point to rotate, right? So I want to just work with what I've got. Okay, so the next thing I'll do is I'll take the point AB and I'll rotate it back to the point C0, all right? Why not? And I think that that should give the Q and the S. Okay, but I've got to be clever about this when I do it. The way because I have to rotate now by minus theta to get back, you see, and that changes Q and S. So what I'll do is I'll put a tilde over them. So when I write this, and I think I'll just begin the writing here, okay? So in other words, I know should be rotating back, but this time I'm going minus theta there, okay, and sine of minus theta there, okay, and then I'll have something like Q and S, but I want to put a tilde over because I want to understand that I need to take the negative of whatever I get, all right, because I'm going back the other way. All right, now A, B, and then C0, so we get C0 in the end. Okay, great. So we just need to expand this. All right, so let's expand it. So we have A cos of minus theta, but I can just observe that cos is an even function, right? So this is just cos of theta. All right, and then next we have plus B, Q with a tilde on it, and that's equal to C. All right, so this one, so sine of minus theta is minus sine of theta. So we'll have minus A sine of theta, and then plus BS with a tilde on it, and this is 0. Okay, great. So this should give us a way to solve for at least S tilde. All right, so let's do that. All right, so S tilde is equal to A sine theta divided by B, right? All right, but A over B, is that a trig ratio? Almost, right? So we can view this as sine theta, because the trig ratio here, if you look at it, it's B over A is tan. Okay, so that's what I want. So let's write this as B over A in the denominator. And so we've got sine theta over tan theta. So now we can cancel, because tan is sine over cos, so we can cancel the sine of theta here and in the tan, and then we end up with 1 over cos, right? Which is just cos. So we have cos theta. Okay, great. So S with a tilde on it, it's cos theta, but since I want to view this in terms of the angle going the other way, I now observe that since this is an even function, I can express this as cos of minus theta. Okay? All right, now let's consider the other equation. So what we have in the top equation, we have the c there. So that makes it a little bit more complicated. Okay, I think what we should do first is divide throughout by a. And we'll write cos theta plus b over a. Q tilde is c over a, right? Because the c over a and the b over a we can replace straight away with trig ratios. Or the a over c, right? So we'll actually put 1 over a over c for that one. Okay, so we have cos theta, we have q tilde tan theta, and then on the right-hand side, a over c was cos, so we have 1 over cos theta. All right, now the tan has a cos in the denominator, so it seems that we should multiply throughout by cos theta here. All right, so we'll have a cos squared there, a sine there, and a 1 there. Right? So, so this gives us q tilde sine theta is equal to 1 minus cos squared theta. And that's just sine squared theta by the trig identity. Cos squared plus sine squared is 1. All right, now we can just cancel the sine theta and get that q tilde is sine theta. All right, but I want to view this in terms of negative theta. And in view of the fact that sine is an odd function, this is minus sine of minus theta. Okay, so now I have this matrix all in terms of, I have everything there that I need, right? But it's in terms of minus theta. So from that, I just infer that the original rotation matrix, A, is just cos theta minus sine theta, and then sine theta, and then what did we have there? Cos. Great. Okay, so I've constructed it. Voila. Yeah, that's right. Yeah, so you're pointing out that you thought that should be minus sine of minus theta, but what I've done is I've done another step at the same time, right? Because remember, so that's what this is, right? So what I would have here is cos of minus theta, minus sine of minus theta, sine of minus theta, and cos of minus theta. But then I go back and think, generally, I want to do this in terms of theta, so I'm just going to invent a new letter, but I'm going to call it theta, and I'm going to replace minus theta with theta. So that's what I did, but I just didn't say it. Sorry? Yeah.
Minus theta, and sine of minus theta equal minus sine theta. Why do you put minus minus?
Because those are the same.
Sine minus theta, minus sine theta, minus sine theta.
Yeah, so the two minuses then cancel out and you get sine theta. Yeah, so these two are the same, right?
Yeah.
Well, that's what I want. But I just want it in terms of sine of minus theta, so that I can refer to the rotation back, all right? And once I've got the matrix for rotating from the point AB back to the point C0, I deduce that the rotation from C0 to AB has to be cos theta minus sine theta, cos theta. So that's what I've done, but it would take a little bit more writing. Okay, now if you don't believe me, I'll just flash another page, okay? And we'll just talk about this from another point of view. So that's the construction of the rotation matrix. Now, if we think we have it already, right, and you can Wikipedia this and you find this, all right? But if you think about, okay, if I'm given this, how can I just verify that that's correct? So you can define a map, right, that sends the vector x to this times x. And then you can just say, I want to show that the angle between the origin and x as a vector and the origin and r theta times x as a vector, show that that angle is theta. All right? And then you could do some other things there. All right, so how would you do that? Well, you could use this formula here, right, for the dot product, because we have 2 rows and 1 column. All right, so let's let y be equal to r theta times x, and let's suppose that phi is the angle between x and y. All right, and our task then is to show that theta is equal to phi. Okay, so here's our dot product as a matrix, and then we have this formula. Okay, so now the y, remember, was r theta x, all right, but let's start with this one. X transpose y, so there's our x transpose, here's our y. Then we multiply it out, okay, and we simplify. And we can see that a couple terms cancel once we multiply that out. And we end up with x1 squared cos theta plus x2 squared cos theta. And that's just the norm of x all squared times cos theta. Okay? Right, but now we have to deal with the right-hand side of this expression and show that these two angles are the same, all right? So what we have next is we take the norm of y. Okay, so here it is multiplied out, but we're just taking the norm of that. And so that's a lengthy calculation there, but we've got a square root. And you simplify it, and you end up with, that's the same as the norm of x. Okay, so you just then sub it into the formula, and you find that you must have the same cosine, all right? So here we're just going to conclude that we have the same angle, right? We know that these 2 points must be the same distance from the origin as well. All right. Good. I think that's just about finished, except for we should really look at these 2 questions in the last couple minutes. But since I want to accelerate a little bit to give people a chance to go to the next class or whatever, I'll just put this up. All right, so calculate the determinant of this. Well, that's pretty easy. We just have cos times cos, and then minus sine times minus sine. So cos squared plus sine squared, and that's 1. So that's simple. Now, if we're to calculate the inverse of this, so we have 1 over the determinant. We swap the diagonal entries and put a minus sign on the other 2. And so we have this matrix here, but the determinant is just 1, so this simplifies quite a lot. But what we want to do is make it look like a rotation matrix. Okay, so we use the fact that cos is even and sine is odd. And so we can simplify it in this way. So what we see is that we just have r subscript minus theta. All right, so the inverse of the matrix r theta is r minus theta. Very nice. Okay, that's all I have for you for now. So If you want to stick around and you're online, you're welcome to stick around. I'll say all this again in the next hour. But meanwhile, I'll go outside and get a drink of water. Thanks, guys.
I'm sorry because I asked you, but I have this one. This next, here we put minus 9 theta, yeah? This is instead of VQ, yes?
Yeah, but I'm dealing with two of them.
Yeah.
Two different ones. Two different matrices.
Yeah, this one, we need to substitute to find this one is following theta is positive, yeah? With counterclockwise. For the next
Yeah, but
one,
then I introduced this. You see, this is a different matrix.
yeah, it's a different.
So this here is a minus theta.
My question is here. Q, here. QX, here we get minus. Here, why we get minus minus? It becomes positive. So why we put minus? So this is my question. Is here Q? We put QX.
Yeah, because I ended up.
Theta.
Yeah.
Yeah. So we multiply again.
Well, I possibly should have used a different letter here rather than theta.
Yeah. So
Right, because I mean, if you.
This one. Yeah,
Okay.
I'm sorry because I'm asking you in front of the student.
What's that?
I'm sorry because I asked you here.
Oh no, no, it's okay because I mean, if you had that concern, then everyone on there has the same concern.
Yeah. Okay. Thank
Right?
you. Yeah. Thank you.
But so this is a different matrix than that one. So I introduce a new one here
Yeah.
to take that back to there.
Yeah. So also, I think you should also show the student that we moved from back. So tan here, tan, it's B over A. So some students they think that why it's tan, why it's not cotan. You look to this theta. So theta it's become here.
Well, yeah, but I'm just looking at the geometry now.
Yeah. This one confused me a bit.
Okay.
Usually this minus here.
So these two are the same, right? Because I pull that
Yeah.
minus out and they cancel and I get this one.
Yeah.
So they're the same. But that's okay, right? Because this just tells me that this is, see, these are all minuses here. So then I get minus sine minus theta.
Yeah.
And down here I get cos of minus theta.
Yeah.
Okay, and so that tells me that the rotation to go back from there to there
Yeah.
is cos minus theta, minus sine minus theta, sine minus theta, cos minus theta.
Yeah.
And so I infer that to go from here to here, it must be, you know, what the rotation matrix is.
Yeah. Yes. Yeah.
So I should slow down and say that.
Yeah.
Next time.
Yeah, this is confusing. Okay.
Yeah.
I think also R inverse is equivalent to R transpose. They put this in Wikipedia, I think, that in rotation matrix R inverse is equivalent to
All
R
right, because it's
transpose.
orthogonal.
Yeah, they put that also.
Okay,
You
sure.
can say that. Yeah, thank
So
you.
I'll just say, and calculate
Yeah.
R theta transpose.
Yeah.
They'll be the same.
Yeah, thank you because I'm discussing on the phone from a student and from that it's okay or not because I
Oh.
confused here a bit why we need to change this sign.
Well, yeah, because I introduce it.
Yeah.
I introduce it because I want to view it in terms of minus.
Yeah.
Because
Yes,
I got
yes.
the diagram in terms of going back.
Yeah, I get it. Thank you.
Okay, so it's 6:01. It's time to start again. G'day, Jonathan. How are you going? But I didn't get my chance to go get a drink of water. I'll be really quick. Okay, so let me have a peek at the chat. Don't know if I can make this any bigger. All right, doesn't seem to be anything significant other than hellos from last session, which I requested. Okay, great. So I think it's just a good time to start. So in this session, we're going over the quiz that you did a few days ago, I suppose. And there were 3 questions. The first question had many parts. And then after that, after we finish going over solutions to the quiz and talking about those solutions, we will consider rotation matrices. So we'll construct a 2x2 rotation matrix and just verify that it's in fact a rotation matrix, and then take its transpose, its inverse, and its determinant. Okay? All right, let's begin. So your first question here considered the function sending pairs of real numbers to pairs of real numbers, and it's explicitly given by f of uv is uv squared plus e to the u plus v, and then u squared v squared. Okay, we also have a function g sending pairs of real numbers to quadruples of real numbers. However, we'll view this as 2x2 matrices. Okay? So it's explicitly given by g of x is equal to f of x times the row matrix 1, 2. And then we've just been given that z is equal to 1 minus 1. Okay, so our first question asks us to evaluate f of z. So we're subbing in this z into this function and simplifying. Okay, so f of z is equal to, maybe I didn't pick up my best pen here. I think I didn't. Try the other one. Okay, so 1 times minus 1 squared plus e to the power of 1 plus minus 1. And then we have 1 squared times minus 1 squared. Okay, so we simplify this and we have 1 plus e to the 0. So 1 plus 1 is 2. And then 1 times 1 is 1. So there you go. Easy marks for that one. Okay, next question. Evaluate g of z. All right, so g of z is equal to f of z by 1, 2. We have f of z, fortunately, so we'll just copy that down. 2, 1, 1, 2. Okay, now we're expecting to get a 2x2 matrix out of this, remember? So let's write one. We have 2 times 1 is 2, 2 times 2 is 4, 1 times 1, and 1 times 2 is 2. Great, so that one's finished. Next question, evaluate the norm of g of z by z. Okay, so this is C. So the norm of g of z by z is equal to the norm of, now we have g of z already, so we'll copy that down, 2, 4, 1, 2. And then z, remember, is 1 minus 1. Okay, so we multiply this out and then we simplify. So we have the norm of 2 times 1 is 2 minus 4. So we have minus 2. And then we have 1 minus 2 is minus 1. Okay, great. Now we just take the Euclidean norm of this. So we have a square root and a sum of squares. So minus 2 squared plus minus 1 squared And that's 4 plus 1 is 5. So root 5. Okay, great. So next one, evaluate the inner product between the columns of G of Z. Okay, so let's write this with this L. I don't know why I said L. Okay, so when you type this in LaTeX, it's \L angle, and L is for left. So this angled bracket, all right? So G of Z. I'll put a subscript there for the first column. Okay, but understand that's what I mean there. So GZ2. Okay, so we're taking the inner product of this, but that is just the first column of 2, 4, 1, 2, so 2, 1, and then we have 4, 2. Okay, great, and then we just take their dot product or inner product. So we could just multiply the rows across and add the result, or you can treat this as a product of two matrices. And so we get 8 plus 2, and that's 10. Okay, good. Now I'm out of space. I'll turn this upside down, and we'll look at question E. Determine the determinant of G of X. And why is that independent of X? Okay, so det of G of X is equal to the determinant of F of X by the row 1, 2. Okay, now at this point, I think I just want to straight away, because I know that this F of X is a column vector, right? So let's straight away say that that is y1, y2. So let's say det y1, y2, and then we have the 1, 2 there. Okay, so you'll notice that I didn't use the formula that's up here. Okay, because this will help in saying why it's independent of X. All right, so we'll simplify this determinant. So we have y1 by 1. So that's y1, and then the next entry is twice y1. Now in the second row, we have y2, and then 2y2. All right, so, I mean, I could just take that determinant, but you can notice here that the two rows are linearly dependent, right? So we're going to have a 0 determinant. But this is just 2y1, y2 minus 2y1, y2. So 0, all right? And since I didn't have to rely on the formula up here for F at all, that is totally independent of the vector X. Okay, great. Let's go on to the next one. All right, which says to find the Jacobian of F. All right, so I'm just going to use my own symbols for this, but there are some conventional symbols for Jacobian, right? And there are a couple of different ones, but personally, my own choice is this one that I've made up. I just put a J and then I put a subscript of the vector function. Okay, and I'll put a tilde there because it's a vector function. And then the point I'm evaluating that at. And so because the UV are there, I'm going to keep the UV there just to make it clear to see. So we'll evaluate this at UV. Okay, great. So we have a formula here. So it is the partial derivative with respect to U of something, and the partial derivative with respect to V of the same something. All right, down here we have partial derivative with respect to U, partial derivative with respect to V. Okay, but in here, here, and here, I've got to take the partial derivative of something And it comes from the F. So the first component goes up there, first component, and then the second component and the second component, right? Where these are, here's my F1, here's my F2. Okay, good. So let's simplify this. But to do so, I'll just write out those functions to make it easier to actually calculate. So F1 is uv squared plus e to the u plus v. And then I'll write that again. Okay, and then we have partial derivative with respect to u of u squared v squared. And then with respect to v, u squared v squared. Hey, Jonathan, how's the audio for you? Do I need to turn the volume up here? It's good, thanks. All right, so we'll simplify. So since this is taken partially with respect to u, I treat v as if it's a constant in that part of the calculation. So here we just have v squared, all right? And then remember the derivative of e to the x is e to the x. But here I need a chain rule, right? So this is not just u to the power of, it's not just e to the power of u plus v. We have to multiply by the partial derivative with respect to u of u plus v, but that's just one, okay? So that's just u to the power, e to the power of u plus v there. I've got a coefficient of 1. All right, now differentiating the same function with respect to v partially, well, we have now 2 uv, and again, e to the power of u plus v. Okay. And in the bottom, we're differentiating with respect to u partially, so we have 2uv squared, and then 2u squared v. All right, great. So that's the Jacobian calculated. So the next problem asks us to solve for x0 . Here we've got the linear approximation. So f with a hat on it is given by this. But we're going to solve for x0 in this equal to 0. So that I haven't written on there, unfortunately, but that's what we've got to do. Okay, so I'll write G down here. So the first thing we'll want to do is calculate the Jacobian of Z, right? Because Jacobian of Z appears right there. So I want Jacobian of our vector function f, and then of 1 minus 1. Okay, so what I need to do is sub in 1 and minus 1 into this matrix here. And so we've got minus 1 squared and then e to the 0. So that will be a 2. And then this is 2 times minus 1 and then plus e to the power of 0. So that is minus 1. And then we've got 2, and then we've got minus 2. Okay, good, that's our Jacobian. Now the next thing we want is f of z, because f of z is right there. So f of z is 2, 1. So that we've already calculated above, but it helps to write it down again. And then let's just write our f hat. So f hat of x superscript 0 is equal to f of z, which is 2, 1, and then plus our Jacobian matrix, 2 minus 1, 2 minus 2, and then we had x superscript 0, and then we had minus z, but that is 1 minus 1. Okay, but what we're doing here, which I didn't say earlier, is solve for this equal to the 0 vector. All right, so we're solving for x superscript 0 in this equation. Okay, so you can see it's a linear equation, but we have some simplifying to do before we just solve it. Okay, so first thing we'll want to do is take the 2, 1 over to the right-hand side. So I'll start over here. 2 minus 1, 2 minus 2, and then we'll have x is superscript 0, but then we also have minus 2 minus 1, 2 minus 2, and then times our 1 minus 1, and then that's equal to the negative of 2, 1, so minus 2 minus 1. And then we'll want to take this over to the right-hand side as well. Okay, but first we need to calculate that. So this is 2, so I'm just looking at this part. 2 plus 1 is 3. And then we have 2 plus 2 is 4. So 3, 4 this is, but there's minus there, so minus 3, 4. And then we take that over to the right-hand side. We have plus 3, 4, and then plus minus 2, minus 1. And this is equal to 2 minus 1, 2 minus 2 times x superscript 0. Okay, so we'll just add this. So that's 1 and 3. And then we just need to solve this system, right? So in the last session, I solved the system by calculating the inverse of the matrix. How about in this one, I'll just do Gaussian elimination to give you some variety if you happen to be watching both sessions. They're back to back, of course, in the same video. All right, so I'll now write the augmented matrix. So 2 minus 1, 1, and then 2 minus 2, 3. Okay, and then I'll put the line there. Now, I want to just separate that, so I'll draw a line, and then I'll move this up so everyone can see. All right, so simplifying or applying row reduction to this, let's see, I want to subtract row 1 and row 2 from each other, but I want that to be in the second row. Okay, now I'll go for a positive number in the bottom entry. So how about then we'll go row 1 minus row 2. Put that in the second row, so we'll get a 0 in the first entry. And then we'll have 1 minus minus 2, which is 2 minus 1 is 1. Okay, and then in the last entry, we have 1 minus 3 is minus 2. And then we still have the 2 minus 1, 1 in the top row. Okay, good. Now we can do some more. So now let's add row 1 and row 2 and make that the new row 1. Just put this over here. It's a little bit messy now. So now we'll have 2, 0, minus 1, and 0, 1, and minus 2. Okay, great. So now all I have to do is divide row 1 by 2. And what we get is 1, 0, minus 1 half, and then 0, 1, minus 2. Okay, so that tells us that x superscript 0 is minus a half, and then here we can just put the 1 and then 4 to be equal to minus 1 half minus 2. Okay, just because this maybe is a little prettier, I don't know. And that agreed with what I got when I took the inverse and multiplied the inverse on both sides. Okay, great. So let's have a look. Have we done all of those? Yes. So that's question 1 finished. Now let's do question 2. Okay, let AB be upper triangular. Calculate EN transpose AB times EN, where EN transpose is the row containing zeros until you have a 1 in the nth place. Okay, so I'm going to do too many calculations here because just to give you a chance to think. Now, your job is actually a bit easier, but you would have to replace my calculations with some well-written English, okay? But so what I'm going to do first is, now these are upper triangular. So what I'm going to do first is write an upper triangular matrix. So A, B, they're both upper triangular. The product is upper triangular. So we have A11, A12, A13, and then we have a 0 and a 0. And incidentally, I'm doing this for 3 by 3, but this is n by n, okay? And the reason I'm doing this for only 3 by 3 is because it's nice and small, but I can get the pattern out of this, okay? And that'll make a nice demonstration for you. But these are n by n, remember. Okay, so I have a 0 there, I have A22, and then I have A23. And then I have A33 there, and this looks just the same, right? So I have B22, B33, and so on, right? Just with B's there. Okay, so the product, I'm going to call the product C. So you can see straight away that this is A11, B11, and you can continue calculating, and what you'll get is A11, 0's down here, of course, because it's still upper triangular, and then here, sorry, B11, and then the next entry, if you go across, and I better write this in. Okay, the next entry is A11, B12, plus A12, B22. And then over here, I have 3 things, A11, B13, plus A12, B23, plus A13, B33. Okay, then below I have A22, B22. And then under here, I have A22, B23, plus A23, B33, and then finally A33, B33. Okay, so here's our 3 by 3 product of A and B. But what you can notice is that there's a pattern in these sums, right? And that's what I want to show you. All right, so if we look at this one right here, we can see the middle two, you know, the 1 and the 1 there, they match. That 2 and that 2 match. Okay, this one and that one match. These 2 2s match. These 2 3s match, and that pattern carries through, right? But the other ones, what are they? We've got a 1 there. We've got a 2 there, a 1 there, and a 2 there. So this is C1, 2, and those match, okay? So the pattern I'm pointing out is that the outsides of these are the same as the index of C, and that carries everywhere through, right? But the sum starts at a given point, right? So here we see the sum starting at 2. Okay, so we can write this in general as a sum, and remember we pointed out that we've got a sum of AI. And then the other one is, let's put a K there. And then here we put a BK. So these two are matching. And then a J, meaning that this is our Cij term here. Well, yeah, the sum is the Cij term, right? So the I and the J are that one and that one. Okay, so where do we start? We begin with K equals I. All right, and that's true there. Now I here is 2, so we're starting at 2. Where do we finish? Well, we finish at J. So J is the column, and that agrees with this. We stop at 2 there, so here we stop at J. Okay, but now I want to say, I mean, this is 3 by 3, but I want to say, just draw a line there and say Cn by n is equal to this n by n, because that pattern continues when it's larger than 3 by 3 as well. Okay, now I've said that I've done too much work, but I just wanted to show you this because it's nice. You might find it useful one day, right? Okay, so now what we're calculating is E n transpose times C n by n times En. Okay, so let's just do the right part of this first. You can't see that, so scroll down. So we'll rewrite the En transpose, and then we'll do this part. Now, this En is the column vector with zeros in it until you get to the last entry, which is a 1. And so when you would multiply this matrix by 0, 0, 1, you would end up with the last column, right? Okay, so this is just the last column of this. And so I'll just rewrite that, except this will be n by 1. And then we'll have to modify this a little bit to reflect that it's just the last column. So the j now is equal to n. We're still starting with I, A, I, K, B, K, N. Okay, now this one was zeros until you get to 1, all right? So if we multiply this by this column matrix here, well, it just takes the last row of it, right? And the last row of this has I equal to n, all right? So I'll just rewrite this. It looks a bit fun. So this is 1 by 1. Oh, hang on, I don't need that one because I'm assuming that I've multiplied this, okay? So the sum goes from k equals n up to n, A, I, K, B, K, N. Sorry, that's an N there in front as well. Okay, but since it starts and stops with N, this is just the the 1 by 1 matrix, A, N, N, B, N, N, which is exactly what you expect when you just think about what's going on here when you multiply this by a column that contains zeros except for the last entry. And then on the left-hand side, zeros until you get to the last entry, which is 1. So really, the answer, what we're getting here is just this. In other words, the intersection of the last column and the last row, okay? So if you could say that really well in English, then you wouldn't have to do this sum that I did, or you wouldn't have to make those observations about the pattern. You could simply make the observation that this is the intersection between the last column and the last row. But you should really try your best to say that correctly. Okay, I think that's question 2 finished. And then our last one's actually pretty easy, I thought. Well, actually, you know what? I thought they were all easy. You might not agree. Some things I find really hard, and most people don't. But we're all different, right? So, yeah, there you go. Okay, so now what we want here. So this is the triangle. No, it's not the triangle inequality. The parallelogram law. So you can draw parallelograms with the vectors u and v. And then come up with a rule. I think I've forgotten how it actually goes, so I won't bother to draw it. I'll just deal with the algebra here. Okay, but what the tool we need here is that the norm of x squared is equal to x transpose x. So that'll be really handy here. Okay, but what I want to do is multiply throughout first by 2 to make the arithmetic look a little better. Okay, so we'll start with the norm of u plus v squared, and then the norm of u minus v squared, and then we've got minus 2 norm of u squared, and then minus 2 norm of v squared. And we're meant to get 0, right? But we're dealing with the left-hand side first. So we'll simplify now. Okay, so using this identity, what we have is u plus v transposed times u plus v, and then we're adding u minus v transposed u minus v, and then subtract twice u transpose u, and subtract twice v transpose v. Okay, now we'll expand these, but before we do, we need to put the transpose inside the brackets, all right? So we have u transpose plus v transpose, then u plus v, and then u transpose minus v transpose, u minus v, and then I'll just rewrite these two. All right, good. And now we just expand. And when you do expand, you need to keep things that were on the left, you need to keep those on the left, okay? So you can't just assume that they commute. These are matrices. So we have u transpose u, and then we have u transpose v, and then v transpose u, and then v transpose v. And that's this one, right? Now you can see the difference between these two is not much. There's a minus sign there. Otherwise it's the same, right? So this the expansion of this one will look a lot like this one, except for the middle two terms will be negative, or have minus signs in front of them. I'm not going to say they're negative, right? Because they have whatever sign they have, but there are minus signs in front of those. So then we write u transpose u, and then minus u transpose v, and then minus v transpose u, and then plus v transpose v, and then let's not forget these two, so minus 2 u transpose u minus 2 v transpose v. Okay, good, and now you probably see that this adds up to 0, but let's just see how that goes. All right, so these two are the same, so we can cancel those. These two are the same, so we can cancel those. We have 2 of the u transpose u's. Well, we have 2 of those here, but they're of opposite sign. Likewise, 2 of these, and subtracting 2 of those. So clearly this is the 0 vector. Okay, any questions so far? All right, so that's the quiz done. Now let's do what we're going to do next, which was to construct rotation matrices. So in your lectures, I suppose, you've been learning about transformations, linear transformations. And that is sending a point or a collection of points to another collection of points via multiplication by a matrix with numbers in it, okay? Right, so let's label this constructing a rotation matrix, and then we'll do other similar things. All right, so I'm going to say, let's let this rotation matrix, so I want to rotate by an angle of theta. So let's say let A subscript theta be equal to P, Q, R, S. Okay, and I want to act on a point to derive what the P, Q, R, and S are in terms of theta. So I need a good diagram. Now, it's admittedly an oversimplified diagram. Okay, so let's first assume I've got this point here and I'm putting it on the axis, and I feel that that's a little bit oversimplified, but well, hopefully it just makes it an easier job for you to follow. Okay, all right, now I want to rotate this by theta, and that goes counterclockwise. So let's put our point, now it should have the same distance. I'll try my best to get the same distance from the origin. Okay, and we know what that distance is, right? It's got to be c, right? Because, for example, if I have my pen here and I rotate my pen from this point counterclockwise, and I end up with a new point at the end of my pen, right? So starting here, going to here. Well, has the length of my pen changed? No, it hasn't, right? So therefore, the distance between this point and this point is the same as the distance between this point and this point, because I'm doing a rotation. All right, so here I'll put in the angle theta. I'll label this point as A, comma B. And then I'll put an arc length of a circle there, just to emphasize that those have the same length. And then let's come down with a dotted line, form a new point, the point A, comma 0, because they have the same x-coordinate. That's what I mean to do, drop down there. All right, now that means that the length of this from the origin to my point A0 is A, and then the height of this from the axis up to the point AB is B. Okay, now I have a nice A, B, and C, which was my plan from the beginning with this diagram. Okay, and so I'm rotating this way. So I want to act on the point C0 with my proposed rotation matrix. So I'm looking at PQRS multiplied by C0, and that gives me AB. And what I want, of course, are what are P, Q, R, and S, right? I'm not interested in what A, B, C, and D are. I'm just leaving those arbitrary for now. Okay, so let's multiply this matrix product. So I have on the left CP and then Q times 0. All right, so that's the top row. Now the bottom row is CR. Okay, so that's the calculation done, and then this is equal to AB. Okay, so this is easy, isn't it? Because I can see clearly that P is equal to A divided by C. So P is equal to A divided by C, and R is equal to B divided by C. Okay, but these are trig ratios. So if you look at this diagram here, A over C is adjacent over hypotenuse. So that's the cosine of theta. And now B over C is opposite over hypotenuse, so that's sine of theta. Okay, so far I have found two of the entries of the rotation matrix. So I'll deduce A theta is cos theta Q, and then sine theta R. Okay, now I don't want to draw a new diagram, but I really do want Q and R. Hang on, that's not Q and R, it's Q and S. Q and S. So what I'll do now is I'll rotate back from AB down to C0. But if I'm rotating back, then what I'm doing is I'm rotating by an angle of minus theta. Okay, so at this point, I'm going to invent a new matrix, all right? So I'm going to say that A minus theta should be equal to cos of minus theta. And then down here we have sine of minus theta. Okay, and then I don't quite have Q because remember I'm rotating the point AB down to the point C0. So I don't quite have Q here. What I have, and I'll call it Q tilde. And then here I'll call this S tilde. And when I work out what they are, I'll just note that in this one, my aim is to rotate by minus theta, okay? And from that later, I'll be able to deduce what this is, what A theta is, from calculating this one. Okay, so let's see. What we have here then is A minus theta, and I'll just copy it out. But notice that cos of minus theta is just cos of theta, so write cos of theta there. And down here, sine of minus theta is minus sine of theta, because sine of theta is an odd function. Okay, and I still have the q tilde, and I have an s tilde. And then that, because now we're multiplying this by AB and taking AB back down to C0. So I'll put an A and a B here, and then I'm going to get C and 0. Okay, good. So let's multiply out the left-hand side. So I have then A cos theta plus B q tilde, and that's equal to C. All right, now the bottom row, minus A sine theta, and then plus B s tilde, and that's equal to 0. Okay, so looks easy to solve for s tilde now. So let's go ahead and do that. So s tilde, so I'll keep this together, so I'm writing a new equation following from the second one. So s tilde then equals A sine theta over B. Okay, but let's notice that this is not quite the trig ratio that I'm after here, because B over A is tan. All right, so I'll express this as sine theta over B over A. And then now I can just write sine theta over tan theta. And then you know that tan theta is sine theta over cos theta. So what we really have when we cancel the sine theta is 1 over cos theta, which is just cos theta. Okay, so in other words, s tilde is cos theta, but now I want to view it in terms of negative theta, right? So I want everything here in terms of minus theta. So I'll use the fact that cos is an even function and express this as cos of minus theta. Okay, good. So now all we need to do is do the top line here and get q tilde. Okay, so the top line, what we have is, what I want to do is divide throughout by A, I think. Yeah, I'll divide throughout by A, so we'll have cos theta, and then plus q tilde. We have B over A, but I can express that as, oh, hang on, I think I want to keep B over A, right? Yeah, I want to keep B over A. Okay, equals C over A. Good, okay, I don't think I've made any mistakes. Now B over A is just tan theta. So cos theta plus q tilde tan theta. Okay, C over A. Now, I want to see that as A over C, right? But so what I do is have 1 over A over C. I think in about 5 seconds, I'm going to need to go get a drink of water. Anyway, so I'll do that, but what we have here is 1 over cos theta. Okay, so now in the next step, we see we've got 1 over cos here, we've got sine over cos here, and so let's multiply throughout by cos of theta. And so what we get is cos squared theta plus q tilde sine theta is equal to 1. And then finally, q tilde sine theta is 1 minus cos squared, but we know that that is sine squared theta. And so we get q tilde is sine of theta. But we want this in terms of minus theta because remember, we're seeking this matrix at this point. And so what we do here is express this as minus sine of minus theta. Okay, great. So what we deduce then is that A minus theta is equal to cos of minus theta minus sine of minus theta hang on. Yeah, sine of minus theta and then cos of minus theta. Okay, great. We're nearly there. Now all we have to do is deduce what we would have if we were rotating the other way, right? So at this point, replace minus theta with theta, and we have A theta is cos theta minus sine theta, and cos theta. Okay? All right. So let me have a look at the time. It's 6:48 p.m. So I'll just show you another page taken from a slightly different point of view. Okay? All right. So this one I've already gotten written out so I can go over it more quickly. So here, let's imagine that we've got y equals r theta times x. Let's let phi be the angle between x and y. Here we've got the dot product and the formula for that involving the cosine of phi. What we want to do is show that theta and phi are equal. Okay, so I expand the left-hand side here with y equal to r theta x, where I've already got it. So I'm just verifying that this is in fact the rotation matrix that rotates any given point by an angle of theta, right? Because in the previous page I constructed it. So here I'm verifying that that's correct using some other techniques, okay? So I multiply these out, and then I multiply this by this, and I get big sum, but various things cancel, and we end up with x1 squared cos theta plus x2 squared cos theta, which is the norm of x squared cos theta. Okay, now what we do is we look at the right-hand side, except we first need the norm of y. Now it turns out that the norm of y is equal to the norm of x. So the right-hand side is just the norm of x squared cos of phi. And so from that point, we can just say, well, we've got cos of theta equal to cos of phi. Those must be the same angles, right? Okay, now the last thing we should consider is what is the inverse of the rotation matrix? All right, now the determinant is quite easily 1. So the inverse is easy to calculate too. 1 over the determinant, that's just 1 there. So we swap the diagonal entries and put a minus sign on the other two. This is what we have, and so this is the inverse of the rotation matrix. But if we want to put that in terms of minus theta, because you can, and then you can view it as a rotation matrix. So we can say, well, cos is an even function, so that's cos of minus theta. And we have minus sine of minus theta, sine of minus theta, and cos of minus theta. And you notice that's just r minus theta. So in other words, the inverse of r theta is r minus theta. All right, Walla pointed out that we could also do this with orthogonal matrices because r theta is orthogonal. So I'll just bring up, this was r theta here. So if you take the the dot product of the columns, you get 0, right? And so you can see that this is orthogonal, right? The norm of the columns is also equal to 1. All right, so this is an orthogonal matrix. And so that means that R theta inverse is equal to R theta transpose because it's orthogonal. So then straight away we get this line, which is, yeah, this is the transpose, right? So it makes it easier to calculate the inverse. You don't have to actually do that part of the calculation when you just observe that it's orthogonal. And you still have to do that, of course. Okay, well, that's all I have for you tonight. Do you have any questions? Okay, great. Thanks, Jonathan. Yeah. You guys didn't have a lot to say, but always feel free to interrupt and ask something. Yeah. How do I say your name? Xuanru. Is that right? It's probably not. How are you going? Yes, all good. And I don't see who else is currently in the room. It might just be the 4 of us, for all I know. Seems like a lot of people show up to the first session, and well, yeah, Walla's my colleague here. So yeah, we've got 2 tutors and looks like 2 students in the second session. So anyway, I hope, since this is recorded and being put on YouTube, that maybe sometimes we say something's better in the first session and something's better in the second session. So somebody could go to a certain point in the second session if they were in the first and didn't understand something, and maybe get it in the second session. I hope, anyway. All right, guys, so I hope you have a great rest of your week and weekend, and I'll talk to you next week. Next week we'll be doing some, well, we'll continue talking about the assignment. So I didn't talk about questions 7 and 8 on the assignment. I'll save that for next week, but we'll have some other things to talk about then too. All right. Jonathan says, yes, I think people are just loading the first session up. Yeah, it looks like it. It's fairly full in here in the first session in the room too. So anyway, all right, good night. I'll sign out now, and I'll see you guys later. Cheers, thanks.